Hello, how are you doing? It's Mike here, and in this video, we're going to discuss how to calculate the arc length of a parametric curve. So we've learned how to calculate the arc length using the derivatives and the formulas given that you have a function. However, the question will often come, what happens when we don't have a function and so we have a parametric curve? So let's go ahead and start with a we'll say, I don't know, maybe a formula or maybe a little bit of a definition, a formula or maybe a little mini definition. So we'll say if no segment of the curve represented by the parametric equations x equals to x of t and y equals to y of t, provided that a is less than or equal to t, which is less than or equal to b, is traced more than once. So we'll talk about what this means. Is traced more than once. Now I'm going to highlight this or underline it in red. Is traced more than once as t increases from a to b, and if the derivative, if dx over dt and dy over dt are continuous functions from a to b, then the arc length is calculated by this formula. So let's go ahead. This is going to look pretty familiar to you because we've seen this somewhat similar when we discussed how to calculate the arc length of a function. So we're going to integrate from a to b of the square root of dx all over dt squared plus dy over dt squared. This is all under the square root, and this is all going to be integrated with respect to t, all with respect to t. I'm sure that some of you are thinking this looks pretty familiar, and hopefully we can read my handwriting, but I just want to make a note here. This is arc length of a parametric curve, and let's just review for our own knowledge. If we want to find the arc length of a function, this is going to be 1 plus the derivative with respect to x squared, and this is all underneath the square root, and we're going to be integrating this guy with respect to x. And we could do this a couple different ways. We could also integrate with respect to y too. So just be careful. We can't integrate with respect to y. We could integrate from c to d, and we would have the square root. Instead of 1 plus dy dx squared, this is 1 plus dx over dy quantity squared, and then we would integrate with respect to y. So these would be arc length of a function. So we've expanded our knowledge, and we no longer have to work in terms of functions, but we can also work in terms of parameters. So let's go ahead and look at an example on how to calculate arc length, given that we have a parametric curve. So let's go ahead and look at an example. So we'll say calculate the arc length. Actually, let's calculate the circumference. Actually, we'll calculate the circumference circumference. Calculate the circumference of a circle of a radius A. Radius A. Oops. Of a radius A. From the parametric, equations. Let's use x equals to a cosine t and y equals to a sine of t, and this is going to be from 0 to 2 pi. So this is only going to have one revolution. That's the neat thing about calculating arc length given a parametric form, is that we could actually see that this exceeds more than 2 pi revolutions, more than one full revolution, or more than one value of 2 pi along. So let's go ahead, and we all know how to calculate the circumference. So we know that circumference of any circle is equal to 2 pi times the radius. 2 pi times the radius. So we expected in this problem to be a. The radius is going to be a value of a because that was given. So we expect the circumference to be a value of 2 pi times a. But let's go ahead and use calculus to prove this. So we know by definition the arc length is going to be the integral from a to b square root of dx dt squared dx dt square plus dy dt squared, and this is all going to be integrating with respect to t. Plugging this in, we're going to have the integral from 0 to 2 pi, the integral from 0 to 2 pi, and we're going to take the square root. First of all, let's figure out what dx dt is, so I'll do this over here in blue. So we're going to have dx dt. We're going to take the derivative of a cosine of t. So take the derivative of a cosine of t, where a is a constant, we're going to have a, but our derivative of cosine will be negative sine of t, and dy dt, taking the derivative of a sine of t, is just going to be a value of positive a cosine of t. So let's plug this in. So we're going to have negative a sine of t squared plus a cosine of t squared, all integrated with respect to t. So this will give us the integral from 0 to 2 pi square root a squared sine squared of t plus a squared cosine squared of t dt. We can pull out the square root of a squared, so this will give us the integral from 0 to 2 pi of a square root sine squared of t plus cosine squared of t dt, and we all recognize the integral, that sine squared plus cosine squared equal to 1, square root of 1 is equal to 1, so this simplifies down to the integral from 0 to 2 pi of a dt. When we integrate a constant with respect to t, we're going to get a t bound from 0 to 2 pi. So plugging in our upper bound, I'll pull out the a, we'll have 2 pi minus 0, which is just going to be 2 pi times a, and that's exactly what we expected our circumference to be, given that we knew how to calculate the circumference of a circle, how to calculate the circumference of a circle from a long time ago, from elementary school. So notice here the neat part about this is that this is not strictly bound for one revolution. Normally, if we were doing this the geometry way, is that we'd only be able to calculate the circumference of a circle, assuming that we're traversing the circle one revolution. But notice, if we were to traverse the circumference 3 or 4 times, 3 or 4 revolutions, we would bound this problem from 0 to 3 pi, or 0 to 4 pi, 0 to 6 pi, 0 to 8 pi. It could be any value that we want. And that makes it a little bit easier for us, knowing that we're not restricted just to one revolution.